Okay, so welcome everyone. Thanks for joining this talk. So today, Nick Swamy is going to tell us about the work that he's been doing on proof-oriented programming. And as many of you already know, Nick has been a pioneer in this area of building systems with provable guarantees. And we're going to hear more about that today. So, Nick, you have the floor.
Thanks, Akash. Happy to be here. I'm going to tell you today about Pulse, a new proof-oriented language embedded within F-star, which is this F-star is the system that many of us have been building for a while to do proofs of programs. And Pulse is a new DSL in F-star based on concurrent separation logic. It's joint work with a number of people, including Gabriel Ebner, Guido Martinez, Tahina Ramanandro, and Asim Rastogi, who I thought I saw on this call at some point, and myself, along with interns who have spent summers with us over the past couple of years. It's going to be a pretty informal talk. Mostly, I'm going to show some code and walk through demos and so on. So I hope you can all interrupt me and ask questions, and happy to have this be interactive. I'll just start with a couple of slides just to set a bit of context. As I mentioned, I've been working on F-star. It's a language that's both a programming language and a proof assistant, and it's designed to enable both sort of semi-automated proof using the Z3 SMT solver, as well as interactive proof using F-star itself and its tactic system and various other techniques like proofs by normalization and so on. The underlying theory of F-star is an extensional type theory. This makes its foundation quite similar to other theorem provers based on dependent types like Coq or Lean. However, this distinction is that these other theories are intentional, whereas F-star is extensional. This is a technical difference which maybe some of you will appreciate, but it's not that important at this level. Broadly speaking, I think the extensionality of F-star makes it easy to integrate with an SMT solver and enables a focus on programming and we use F-star to build general purpose programs with effects like state and exceptions and non-determinism and so on. As I mentioned at the beginning, you can use it as a programming language or as a theorem proving tool. F-star is used at scale in a number of. I'm just going to try to hide these controls here. If I can move this. Right. Okay. It's used in several production systems. We've built a bunch of code in F-star. Maybe in our CI system, we have a dozen projects totaling maybe a million lines of verified code, some of which is deployed in Linux, in Python, in Windows, in Hyper-V, and so on. So a lot of this code has been is generally geared towards sort of low-level security critical applications, things like cryptography or low-level parser generators or boot frameworks for IoT systems, things like this. But despite us being able to build all these proofs at a somewhat non-trivial scale, proofs are still extremely hard, and they require a great deal of expertise. And even for experts, the effort is still very substantial. And I think ultimately there's no real silver bullet in trying to make proofs easier. There's just I have some thoughts about progress along various dimensions, but just a few remarks here. F-star embraces SMT solving. SMT solvers reduce the proof overhead somewhat, but SMT-based proofs can be a bit opaque and brittle. So when it works beautifully. When it doesn't, you might be left, staring at a proof that you don't quite understand. Um, I I think most people would agree that purely functional programs are easier to verify, whereas a low-level imperative code is harder because you have to reason about pointers and heaps and so on, which makes things difficult. And once you add features like concurrency, then the problem becomes even harder still. So, in terms of progress, I think I think of it in along three main dimensions. The first is, given that doing program proof is so challenging, one has to carefully pick high value verification targets so that the effort is justified. And as I mentioned, we've been picking domains where we think there are a large number of potentially security critical bugs that would benefit from formal verification. So that's in areas like you know um, uh, it, it, secure handling of attacker controlled inputs with verified parsers and serializers, or kernel drivers, or policy engines, or things like this. So choose your targets well. Um, Recently, in the last couple of years, there's of course been a lot of excitement around AI, and maybe AI will help in reducing the proof overhead somewhat. Uh, and maybe not just in proof overhead. It maybe AIs can help us specify programs um, and also do program synthesis. We have some recent somewhat encouraging evidence in this direction, but it's still very early days. There's lots of work to do still to assemble data sets, uh, of which there's still not nearly enough when in comparison with um, general purpose programs in, say, Python or um, TypeScript or something. So data sets of verified programs are hard to come by. We have some. There are others available in the ecosystem of different programming languages, but each of these is kind of separate and siloed. You might learning how to do a cock proof is not nearly the same as how you do a proof in, I don't know, say Isabelle, though there are some similarities. So finding ways to help to kind of aggregate all these data sets and maybe teach models to reason in some way is, I think, an exciting and important direction for the future. Though one will have to see if the models really continue to improve at the rate that we hope they will. Um, but I think, and this is what my talk will mostly be about, which is, I think there's still a lot of work to do on the foundations and the tools, and we need to find ways to sort of raise the level of abstraction in which these proofs are conducted. And one way to do that is as has been the case for the past, I don't know, 20, 30, 40 years, is to find higher level logics in which one can do more structured program proofs with better automation, better symbolic automation, and perhaps even things like program synthesis and code generation from specifications. So I'm going to focus on that bit today, and specifically about Pulse, which, as I mentioned in the beginning, is a new DSL based on concurrent separation logic, a foundational logic for program proofs. It's less reliant on SMT solving, although it still uses FStar's Z3 integration. It's much more, how shall I say, much more sort of sparing in its use of the SMT solver as opposed to default FStar, and focuses on making many small targeted SMT queries rather than large queries that involve many different theories at once and so on. And we've also been kind of rethinking the user interface, focusing more on some kind of a fine-grained incrementality and with full visibility of the current proof state for the programmer. So I'll show you some of that. And you write your program in Pulse, and when you want to execute it, you can extract it to, depending on which features you use, you can extract it to either C or Rust or OCaml, or even if you're writing GPU programs, you can extract it to CUDA. So we have a paper coming up at PLDI that's about the underlying theory and the logic of Pulse. There's a link there at the bottom. The paper is quite a bit more focused on the theory. I'm going to spend the rest of my time in this talk in a code buffer, giving you a flavor of how Pulse works. So before I jump in, that's maybe a time to pause, and if anyone has any questions or thoughts, I'd be happy to hear from you.
Yeah, can I ask a question?
Yeah.
I was trying to find the raise hands button, but I wasn't successful for the last minute or so. Anyway, why concurrent imperative programs? Your earlier slide said functional programming is easier. So
Why imperative?
functional programming?
So FStar has always been a mixture of functional and imperative programming. We tend to use purely functional programs for specifications, but ultimately to get efficient low-level executable code that we can compile to C or Rust or even assembly, for better or worse, extracting that kind of performance requires being able to write imperative programs. Okay. How's Pulse different from Iris? Yeah, you'll see. I think you'll maybe see as you go, Chandradeep. It's very much inspired by Iris, and but it's built on a different foundation. It gives you, if you're familiar with Iris, I think you will find the concepts of Pulse very familiar. It has invariants that are impredicative. It has invariants on names and have invariant masks, and there's some notion of atomic computations and so on. But rather than in Iris, which maybe some of you know about, is an extrinsic logic for deeply embedded programs, whereas Pulse is an imperative, is an intrinsic logic for shallowly embedded FStar programs. Maybe on questions about, like, I haven't really said anything about Pulse yet, so hold on to about your Pulse questions, because I think I've only just given you the Pulse teaser. So let's have a look at Pulse a bit, and then you can ask more Pulse questions.
So Nick, can I ask a question, which is not related to other things? So you mentioned that you have gone away from using large SMT queries. Can you expand a bit on that more, like particularly what, with one example maybe, or you'll talk in this if you're going to talk?
Yeah, I can mention it now. So typically the way many tools work, including those based on say Boogie or Daphne, which compiles to Boogie, is you write a program procedure, and then the tool computes a single verification condition for that procedure, so like a weakest precondition for that procedure, and then that takes that large formula and encodes it to the SMT solver, and that single formula contains all the proof obligations of that procedure, every loop invariant that has to be proven, every assertion, and everything is in that one large query. Now, when you default FStar also behaves this way, although FStar has this behavior where it will compute a weakest precondition for your procedure, but rather than sending it all to SMT, there are ways in FStar that you can say, for these assertions, don't send them to SMT, solve them by tactics, or these assertions, solve them by normalization, or so on. But the general framework is similar. It computes a large VC for a single procedure.
Yeah.
Now, what this means is that the SMT solver may struggle to prove one assertion among many, and cause the whole verification condition to take a very long time, or to be brittle, It may work if you are under a certain random seed, or if you tweak the program slightly, maybe that VC starts to work again. Because SMT solvers essentially are trying to solve these, undecidable problems involving, once you have theories like nonlinear arithmetic, or you're relying heavily on quantifier instantiation, all of this can get quite brittle. Now, what Pulse does instead is, rather than computing a single large VC for your program, it will compute the assertions. The Pulse checker, as you will see, goes in a very structured, fine-grained manner. It has a kind of a forward symbolic execution through your program, and will ask SMT solvers, it will ask Z3 specifically queries that are about individual assertions in every line of program text separately, making the search space for the SMT solver somewhat smaller, and the whole thing more predictable. Like if the SMT solver fails, you know exactly which assertion failed. And an assertion on line 5 cannot somehow influence the behavior of a query at line 2.
Okay. So basically, there is a symbolic execution engine which is basically using the solver at different points in the program, rather than converting the whole thing into a formula and throwing it to a solver, or using
Exactly.
it. Okay, good.
Yeah.
Thank you.
All right, so actually, I just wanted to say that so I'm going to be mostly in demo mode, but you folks can follow along in VS Code if you're so inclined. So let me show you how to do that. So if you go to star lang Pulse tutorial 24, I'll paste this link here. I can paste a link chat there. There you go. And if you're here, what you can do is you can open up a code space. I had one open last night. So if you click that green code space link, this one again, I'll just pull it up. If you click on this, if you haven't clicked on this before, you'll have a green button. You can click on New Workspace, and that will create a workspace for you. And then you should have a VS Code instance in your browser with in which you can run Pulse and run FStar and so on. So it'll take a minute for it to load up, but I'll let you do that in the background. If you try this and you have trouble with it, you can ask me a question, and maybe I can unblock you. So let me start with my demo. So here's what FStar looks like. This is FStar running in VS Code. By the default kind of look and feel of FStar, I wonder how many of you have tried FStar before. I see some familiar faces, but I imagine not all of you have seen FStar before. Its default look and feel is like like OCaml or F# or some other functional programming language. So you can do things like you can write map over a list, and here's a recursive function map that maps a function f from some type alpha to beta. Tick A, I pronounce it alpha, and tick B beta. So a function from alpha to beta, and given a list whose elements are of type alpha, map will walk the list, and if it's an empty list, we'll map it to the empty list. Otherwise, it will apply f to the head and recursively map f to the tail, and produce a list of beta. And this is a if I leave out a case, let's say FStar will complain saying the patterns are incomplete here. Okay, so that's basic functional programming in FStar. So you can also do folds. I'll start to go a bit more quicker. Fold essentially applies a function f, accumulating it over the elements of a list with some initial value x. And here's a fold. And what's interesting about FStar compared to other functional programming languages is that you can assert properties about your program at compile time. So I can say, if I map the increment function, lambda fun x arrow x plus 1, fun is like the lambda constructor, to the list 1, 2, 3, I get 2, 3, 4. But if I make a mistake here, like suppose I forget the 4, it will complain saying that this assertion failed, and this is an assertion failure at compile time. Of course, it's not just only assertions about. I'll use this a little bit, so I may as well tell you about it now. If a program definition is expected to fail, you can decorate it in F star with expect failure, and it will check that it actually failed. So that's one way to sort of write small unit tests inside your program. But it's not just assertions about concrete values. You can do kind of symbolic theorem proving inside F star. So here's a little helper. F dot G is the function composition of F with G. And then you can do proofs about symbolic proofs about all executions about your program. So for instance, here's a little proof by induction that if I have a list L and functions G and F, then if I map G over L and then apply the fold of F, this involves 2 scans of the list, because I'm first going to walk the list applying the map, and then I'm going to walk the list again to apply the fold. What this lemma is a keyword in F star that says what follows here is a property that's true about your program. And so this lemma says that instead of walking the list twice, you can compose the functions F with G and walk the list just once doing a fold, and these 2 things are equal. And so this is sort of map fold fusion. You can fuse the map with the fold. It's a common kind of program optimization. And you can do this proof in F star by induction, where if the list is empty, then there's nothing to prove, because both sides just reduce to the empty list. Sorry, just reduce to the initial value. And if it's a head and a tail, then you just call the induction hypothesis on the tail, and F star plus the SMT solver can figure out how to complete the proof if you just give it the induction hypothesis. So that's kind of default functional programming in F star. Any questions about that? Okay, so instead of so now let's switch to Pulse. So the way Pulse is embedded in F star, and you enable Pulse by just saying #lang Pulse in your F star file, and then whatever follows can be a mixture of traditional functional F star together with some new imperative features. So I open up the Pulse library, and then now if I want to write a program that is that does a imperative increment of a reference to an integer, I can write it this way. And what this is saying is that I have a function, an imperative procedure, incur, that takes x, which is a reference to an integer, as an argument. And it's got this requires and ensures, which are going to be specifications in separation logic. So in separation logic, there's one of the basic building blocks is this thing called the points to predicate, which says here that the precondition of this function is that it must be called in a heap where the reference x points to some value I, tick I, and tick I is like a logical variable. I don't have access to it in the executable fragment of my program. I just need to know that there's some value that x points to in the initial state of the program. And the post condition says that after this procedure executes, x will still remain in the heap, but the value it points to will be 1 greater than the value it pointed to initially. Okay, so and the way the implementation of this program works is bang is dereference. It reads the current value of x and then assigns the next value to x. And the way this works is that f star will the pulse checker, as I mentioned earlier, will start with the precondition as its symbolic assertion at the initial state and symbolically execute the program, pushing this precondition through each command as it each command or each line of the program, checking to see if the current assertion is sufficient to prove the correctness of the line that follows, and then compute the next assertion and so on. Throughout this process, you have access to you have visibility into what the solver is doing. So at every point you can say, well, at this point in the program, what the solver knows is that x points to I, and this value v that was just read from the reference, we have a pure fact that I is equal to b. So you can observe this this program state as the solver goes, and use it to understand how to continue your proof. Next example. So a points to is one of the basic building blocks in a separation logic. The other one is a way to combine separation logic propositions using what's called the separating conjunction, or in Pulse, this is written using 2 stars. So I pronounce this just points to x v0 star points to y v1, which means that which means the precondition of this program is that it must be run in a heap where there are 2 disjoint heap cells, x and y, and x contains the value, the heap cell that x points to contains the value v0, the heap cell that y points to contains the value v1, and the postcondition of the program is that the values are swapped. And this works for references of any type A, and you can it's a polymorphic swap. So any questions?
That single quote, what does it mean?
Sorry, can you say that again? I couldn't hear you.
The single quote before
Yes.
What does it mean?
The single quote is it's similar to this. So for instance, here we had a single quote before the A, and this is saying this is an implicit variable that whose type f star is going to infer. So in the case over here, single quote A is just some type, whereas here single quote I is an integer that's in scope. So it's just a way to bind an implicit variable that an implicit logical variable. So I could also have written it this way. So this would have been equivalent. I could say and what this is saying is that Inker takes, as usual, takes my x, which is a reference to an integer. It also takes an implicit variable I, whose type is erased int, meaning that I is not going to appear in any concrete execution of the program. The compiler will erase it and must erase it. And it's only used for logical specification. So this is the explicit way of writing things. And tick I is syntactic sugar for writing this. Does that answer your question?
Yes, yeah, thanks.
Okay.
So Nikhil, could you also say, I mean, this x is assigned v plus 1. Can you just say x is equal to x plus 1? Is that allowed?
It's not allowed currently. I think you're asking about this. Could we do this, right? It's not allowed currently. Pulse insists that there's at most one effectful expression in every effectful sub command in every line. And over here there's 2. There's a effectful read and an effectful write, and Pulse will force you to sequence these.
Okay, and I need that shriek X to read X, to dereference X.
To dereference X, you need this bang in front of it. This is similar to this convention is from OCaml.
Right, but when I assign to X, I don't need to dereference it, is it?
Yeah. So the colon equal operator, here's its type. It says its first argument is a reference. So the left hand side of it is just a reference. You don't need to put a star or a bang or anything on the left.
Mhm. But even a normal integer assignment is also with a colon equal to.
A normal integer assignment. The colon equals is so you can do this.
Okay, that is just okay.
Yeah, let y equals 17. You can just do that.
Mhm.
But y is not mutable. Y is just a pure. You can't assign to y again. The only way you can assign to something is if it is a reference or a few other kinds of mutable things. If it can be an array or a heap reference or things like that.
Okay.
There's a question on chat.
They actually the requires and ensures eventually I'm hoping that I have till 8 o'clock. I have 55 minutes or so, right, Akash? When does it end?
I think we book it for an hour and a half. Deepak, is it okay? Will people drop off after an hour? What do you recommend?
Yeah. I mean, I think we are hour and 10 minutes should be okay.
Well, let's see how far I get.
You can continue. Yeah, I mean, whoever's wants to drop off first, welcome.
Yeah, I'll just see how far I can get in what time we have. But Chandradeep, I'm hoping I will show you that these specifications can be very expressive. So these requires and ensures they involve like full separation logic with existential and universal quantification and magic wands and invariances, so that you can say anything you want in these specifications. They're powerful enough they're as powerful as Iris. So here's how so I showed you how you can mutate references. The way you allocate them is you stack allocate references. This is a bit like Rust, maybe. So you can, if you declare a variable as mute, so here I say, let mute x equals 0, y, and let mute y equals 0. Now, the type of x and y are going to be, if I look at my proof state, I'll see that x and y both have type ref int because they declared as mutable. And I can do here, I can do things like, y colon equals 17, and then and only then, and can I assign to it, and then these two variables are implicitly deallocated once the stack frame exits. You also have heap allocated references, so you can do things like, again, this is kind of a bit rusty. If I want to allocate a reference in the heap, then I call box.alloc, and what I get is something of type box int, and these things live on the heap. And if I have a boxed reference, then I can explicitly call free on it as well. And of course, if I try to do something silly like a double free, then the checker will complain saying, you've already freed it. At this point, I only have the empty assertion in my context, and you're trying to prove box.points to, that doesn't work. Okay. Likewise, if I say I forget to free it, Pulse will complain saying, you claim that you're returning no resource. You claim that you're returning the empty resource, but here you have a leftover resource, box.points to, did you forget to free it? So And let me go a little bit quicker, so you can do swaps with boxes too, of course. So the general spirit of things in Pulse is that you write specifications as pure F star functions. So here's a pure function called max. I'm going to call it max spec to compute the maximum of two integers x and y. And what you do is you can write a Pulse program whose specification says that it is a refinement of the pure specification. So here suppose I want to find the maximum of two references, x and y. It turns out, so there's two things going on here that I wanted to show you. So the first is that to compute the max of two references, I don't need to mutate the references. So I don't need full permission on the references. So this points to predicate in Pulse is indexed by a permission, which is it's actually a fractional permission. So if I want to write a reference, I need ownership of the full fraction, a complete, the fractions range between 0 and 1. And if I want to write to something, I need full ownership. I need 1 as my fractional ownership of a points to assertion. If I only want to read something, then I don't need full permission. Any permission will do. And so Max is saying, so long as I have some permission on x and y, that gives me permission to read it. And Max is going to return some integer n such that x and y still point to the things that they were pointing to originally, but n is equal to the maximum of x and y as specified by this max spec function. And that's this style here, and maybe this is also getting at Chandradeep's question. You can also write arbitrary F star predicates enclosed within this pure connective to relate values in the separation logic to pure F star values. So here I say this return value n is equal to the max spec of Vx and Vy, which is showing that in a way that Max refines max spec. Of course, it's not, so maybe let's have a look at our first loopy program. Is this still visible if I reduce it by 1?
Yeah, it's visible. Yeah.
Okay. So here's a program that's going to it's a classic example. I think multiply by repeated addition may have even been the example that Turing used in a paper from 1950 describing his maybe even earlier actually. Possibly the first paper about program proof. That paper was about multiply by repeated addition. Where what I'm going to do is I have two numbers x and y. They're both natural numbers, which means they are at least 0. And this function is going to return some number z with the proof that z is equal to the multiplication of x and y. And the way it's going to do it is it's going to have a counter and an accumulator, and it's going to loop adding y to the accumulator x times. And so here I have a while loop looping until the counter reaches x. And I can write my invariant that says through every iteration of the loop, the counter points to some value c, the accumulator points to some value a, and they are related by this condition that says that the counter value is always less than or equal to x. The accumulator is its current value is always c times y, and the loop continues so long as c is strictly less than x. And once I exit the loop, I know that c is equal to x. So then the invariant is going to give me that a is equal to x times y, which is what I need to complete the proof. So at any point here, you can say, what do I know? And here I'm going to know that I know that, let's see, let's just look at it here. Just as I enter the loop, what I have is the loop invariant Here we see our first existential quantifier. So that's exist star is a separation logic existential quantifier that quantifies C and A over the scope of this predicate. And then when I exit the loop, I have to restore this predicate. Questions? I'll keep going. So you can, of course, I'm not going to go through this one in detail, but you can, rather than computing over natural numbers, you can also compute over machine integers. So here's Fibonacci computed over machine words of 32 bits. And here, this proof is a little bit more interesting because I have to prove not only that I compute the right answer, but that in doing so, I never cause integer overflow. For that, I need a precondition that the mathematical value of Fibonacci on K fits in 32 bits. And if I have this precondition, I can actually prove that all the arithmetic that I'm doing here never overflows. And in order to do this, I need a little lemma that tells me that that Fibonacci is monotonic in a sense, which is that if m is less than n, then fib of m is less than or equal to fib of n. Sorry, both less than or equal to on both sides. And I need this lemma so that I can show that if I know that fib of k is less than 2 to the 32, then as I'm computing up to fib of k, I still have no overflow along the way. And I can do that I can define lemmas in F star and just call them in pulse, and that works out. Now, I just also wanted to show you that you can also, having written all this code in pulse, what you can do is also extract it to C, or so here I've taken this Fibonacci function and put it in a separate file, and then I can I ran this make command before, so I already have the output. So you can extract it to C, and if you extract it to C, what you get is, in all cases, what happens is that F star erases all the proof content, and what you're left with is just the executable code. So you can get C code out of it. We also have a tool that lets you get Rust code out of it. And you can also extract the same code to OCaml, which is kind of the default backend of F star. And
are there any guarantees on the extracted code?
So the guarantees on the extracted code are that, what we do is, I mean, yes, otherwise this whole exercise is pointless, because this is the code that you're going to execute. The guarantees on the extracted code come with trust in our tool chain, so that our compiler actually, did not erase some part of the program that is actually needed, let's say, or didn't transform your program terribly. So it is you have to trust the F star tool chain that its compiler behaved the correct way. But we have a formalization of some of this. So what we do is in a ICFP 2017 paper, what we did was we formalized a subset of C, one of the intermediate languages of CompCert. We formalized it as a target of compilation of an intermediate language of F star, and proved that compilation is a simulation. Although that compilation, that proof is a pencil and paper proof. And the tool that actually does this compilation is the F star backend plus an extractor tool that we have called Caramel, implemented by Jonathan Protsenko. So both these things are in your trusted computing base, but this is the code you execute. So the proofs that you're doing are, in a way, about this executable code.
Okay, thanks.
Any other questions? So let me go to the next bit of my demo. So here's a really I wanted to show you that you can define your own predicates and use them. So here's a really simple example. So let's say I have a two-dimensional point with two mutable fields x and y. I can define my own predicate is point and say that the point P, its values are two integers x and y, and the predicate is, so here you see that the first time I've shown you the type SL prop. So the type of predicates in Pulse are called SL prop or separation logic propositions. And this is the language of specification in Pulse. And it contains all these connectors that I showed you earlier, points to and star and so on. So SL prop is an F star type like any other type. So you can quantify over it and make definitions about it and so on. And is point is a predicate whose definition is this conjunction of separating conjunction of two points to's, saying that the x field of the point P points to x and the y field points to y. Now, if I want to say move my point, suppose I have is point P x y, and I want to move my point by some offset dx and dy, then the way I can do that is I first unfold so let's look at my proof states here. So initially what I have is just is point, and now I want to read the x field, and let's say I do that. This dereference is going to complain and say, by default, it's going to say, I need to prove that the reference I need points to on p dot x, but in the context, I only have is point. And the default behavior is that Pulse will force you to be very explicit about how you fold and unfold your predicate. So if you unfold is point, now I have, in my proof state, I have the definition of is point. And now I know that p dot x points to x and p dot y points to y. And now I can do the dereference. Okay, so likewise, at the end, if I don't put the fold as point, I'm going to say that the checker is going to say the goal is point P x plus dx, y plus dy, but I only have this in my context, and I need to explicitly tell the checker to fold things up and give me back is point. Okay, so this is this bit about very fine-grained incremental control. We want the programmer to have control over how predicates are unfolded and not, and so really, like, Pulse is much more geared towards, like, control over full automation, as we want to tame the brittleness of proving at scale that maybe some of you who have been using F-star before have experienced in larger developments. So everything is very much in your control in Pulse.
So this fold, is it like a wrap, unwrap kind of?
That's right. Fold and unfold are wrap and unwrap for definitions.
Okay, so it doesn't let you change it until you unwrap it.
That's right. Now there's various things you can do. So I'll maybe you can you can mark a definition saying implicitly unfold it, and then it will unfold it for you. I mean, so there's various kind of bells and whistles that we have to control this behavior, but the default is that you have to do it yourself.
So Nick, I have a question about the specification language itself. So yeah. I see that this Pulse is combining some notion of Rust type checker of borrowing and basically giving safe mutability and sharing. So traditionally, when we're programming in, let's say, a refinement type system, if there are references, you can't use those references themselves into any specification. So basically, But some of the Rust extensions for refinement type extensions for Rust, they do allow to use these references as well in the specification by some kind of indexing thing. They basically use the guarantees given by the underlying Rust type checker to write richer specification to capture the properties of the system. So is Pulse is also in that direction, or that's not yet? Are you using the Rust type checker itself, Rust kind of type checker itself to write specifications?
So the syntax looks maybe inspired by Rust, but actually, what's happening is, Rust is based on this. It's based on a linear type system, and it's the borrow checker is this syntactic borrow checker that's trying to check that you're using your variables in a manner that is respecting Rust's ownership discipline. In Pulse, so this, but by the way, this whole linear types and ownership in Rust is the underlying foundation of it is kind of the logical foundations of it are in separation logic.
Mm-hmm.
In Pulse, what we are doing is we are directly building on separation logic rather than going through linear types. So what you write in all these specifications in Pulse are just directly in separation logic. So all the ownership checking that's happening is not through a discipline of borrow checking with linearity as happens in Rust, but it is just through separation logic proving. So the end feel of it is maybe a bit like Rust with this readable and writable and mutable borrows and things like that. But the foundation of it is very different. It's done over separation logic. So now your specific question about refinement types and not being able to write specifications over like the contents of a reference. This is the way that we are getting around that in Pulse is. So notice, like if I go back here, if I just go back, let's look at my very first the increment example here. In default F in some pseudo F star, let's say, like suppose I just write incur spec, and here I want to write here, somehow I want to write that. The value of the reference at the end of the program is 1 greater than its initial value. Maybe I want to write something like, result. You can't even write it. You can't even say, is bang x plus 1 or something. There's no way to write this in most languages that have refinement types. So the way we get around that is by using these assertions that give us that tie the value of the reference in the current state to some logical witness I. And then we can write specifications that speak about the current value by using this logical witness I. So I think some of these systems that are using refinement types for Rust, what they're doing is they're exploiting the fact that in Rust, a reference to an integer is just a linear value, and you can just disregard the fact that it's actually pointing to some memory. You can just treat a reference to an integer as just an integer and use it in specifications. This we do not in Pulse. We don't have this. You have to go via the indirection of a separation logic predicate.
But that makes sense because it's much more powerful language anyways. Okay.
It's an interesting question. You can have a long discussion about the various styles of specification and proof in this space. Any other question? So that was that's just curious. Right. If how does it handle aliasing under the hood? So So let's go back here. So maybe I can just show you an example from, and just write an example here. So let's say I have a uh, I don't know example. I have an x of type ref int, and I want to I have a points to predicate on it, and I want to return 2 copies of it. So I can do this. So if I have a points to predicate, I can make 2 copies of that points to predicate so long as I halve the permissions associated with it. So now I have 2 points to assertions, and now I can sort of make an alias to it by saying I'm going to return some other reference S, and one of them has points to S. So I think I can do it this way. Hold on, I might be able to. I can return it. Sorry. So now I have, if I now let's say call the x. And let's say I do s equal, let s equal exr. At this point, I have S and R, they're both references, they're aliases to each other, and they have points to predicates for both of them. So, but if I look at in some more detail at what kind of arguments I have, then I have 2 of them, but I have only half permission on each of them. So I don't know if that answers your question, Durvasa. It's you can create aliases, and the separation logic is going to track how much ownership each alias owns. Are the fractional permissions similar to Viper? So fractional permissions are they date back to work by John Boyland in the late 90s, early 2000s. Many systems have fractional permissions. In Pulse, the fractional permissions turn out to be a special case of something more general. Pulse has an extensible way in which you can define ghost state of whatever of various different kinds that you can use to model different sharing disciplines, and fractions happens to be one such ghost state construction. So they are Viper also has fractions, but I think fractions in Viper are kind of built in as opposed to being user defined and extensible. So let me see how much. I'm kind of at the end of time, aren't I? So I haven't really gotten to any concurrency. Multiplication by addition code is available. All this code is available. It's a I can paste a link to it here. I haven't gotten to any concurrency. So, but I mean, it was fun talking about all this stuff anyway. So if you all
Yeah, I think Nick is okay if you want to go for 5-10 minutes. Maybe you can just introduce concurrency a little bit.
yeah, how about I jump ahead to concurrency a little bit? So let's see. All pulse code is inherently data race free. So if I have if I try to update a reference and I try to do a parallel update of a reference. So here's this construct in it's a library function in Pulse that lets you spawn two threads and run these two pieces of code in parallel. So parallel update. What I'm trying to do is I have a reference to an I, and I'm trying to update it in two threads at the same time. And here, what Pulse is going to say is that, well, one thread, say the first one, it consumed the points to permission, and so the second thread does not have access to it. Two threads cannot have full ownership of the reference at the same time. So everything is data race free by construction. So now, if I wanted to do a parallel read, this I can do. So read into is going to say I have a reference X and an out reference out. I have only some fractional permission on X, but I have full permission on out. And what read into is going to do is it's going to read the value of X into out. And this I can do in parallel. I can because I only need read permission on X. What I can do is, let's say I have say I want to read X in two threads and return like sum the values of the two reads. So what I can do is I can allocate two out references, out L and out R. And then I can share my ownership of X. And so after the share, I'm going to end up with two copies of X, two ownership assertions on X, but half permissions on each of them. And this I can share between two threads and run these two things in parallel, and then and give full ownership of out L to the left thread and full ownership of out R to the right thread, and then gather up the permissions again, combine permissions to the two copies of two half permissions of points to an X, and this works. So I can do parallel reads. But how about, I mean, sometimes you actually want to be able to do, writes in parallel, and if you're going to do that, then you have to have some means of synchronizing the writes. And one thing you can do is Pulse has a notion of atomic operations, and an atomic operation, which the Pulse library comes configured with a few atomic operations. So write atomic is a Pulse library function that is an atomic operation to update a reference to a 32-bit integer in a single atomic step. Okay, and atomic operations are qualified with this atomic keyword. Now, if I want to write, I'm allowed to do atomic writes to the same location from two separate threads, because that doesn't race, because the operations are atomic. So, but I still need some way to share permission to my mutable memory location between the two threads. And one way to do that is through this notion that Pulse has of an invariant. Now, if you've seen Iris before, Iris also has some notion of invariant, and the Pulse notion is quite similar. So what you can do is you can take any predicate and turn it into something called an invariant. So say I have here I have X points to I, and I can turn this predicate into an invariant, and I get a different predicate called in I, and and I've defined owns here. Owns is just the existentially quantified points to predicate. It says that X points to some value V. That means if I have, and it's full permission to X, and owns X is this assertion that I have full permission on X for some value of its of the reference. So once I have an invariant, invariants come tagged with it. Every invariant has a name, and that name is called an I name. Okay, so what I get here is this invariant predicate, and once I have an invariant, I can freely share an invariant. So there's this library function called dupe_in, that if I have an inv I for any predicate p, I can get 2 copies of it, and so that I can give a copy of the invariant to different threads. So invariants are shareable, and now the interesting thing is, once I have an invariant, what can I do with it? So it turns out there's a conceptually, what you can do with an invariant is you can open it within the scope of a single atomic instruction and make use in that context of the payload of the invariant. So let me show you a little bit how that looks. So suppose I have an inv I owns X, and I want to update this reference. Then what I can do is, let me hide some of this for the moment. And if I do with invariance I, so let's look at the proof state. So initially I have inv I owns X. And if I do with invariance I have a block here, and within this block, the proof state changes. And what I have within this block is what was initially owns, here I had inv I owns X. As soon as I've opened the invariant here, what I have is later owns X. So it turns out this later is, again, for those of you who've seen Iris, maybe this is familiar. Later is a way in these separation logics to control how invariants work, to prevent certain paradoxes in the logic. So what you get is you get this predicate owns X, but guarded under this later predicate. And what you can do is you can eliminate this later predicate. And once you do that, you will have in your proof state, now finally you will have owns X. Once you have owns X, you can make use of it. You can unfold it, and that's going to give you the underlying predicate. Now you can write your atomic value, and now you can fold the predicate back, and you have owns X again. And when you exit the invariant block, you must once again establish later owns X. And this later intro is going to do that for you. And at the end, you have here later owns X, and now you're allowed to exit the invariant block. Okay, so with an invariant, you just to summarize, you can open it in a single atomic instruction. You can make use of the predicate of the underlying payload of the invariant. So with this, if we go back to my attempt to update 2 references in parallel, if I have a single shared location X, I can create an invariant for it, and then share it share that invariant so that 2 threads can separately access the invariant and mutate the reference and restore the invariant. And so I think I'm going to stop there because and maybe just take some questions from you guys, and just say that these invariants are the basic building block on which all the concurrency features of Pulse are built. There's the underlying separation logic that enforces by default data race freedom and ownership, and then to actually enable synchronization among threads and to share ownership and so on. These invariants are the key mechanism, and using it, you can program all kinds of other synchronization devices. For instance, here what I have is how you can program a lock out of using as a primitive. You're going to suppose you have just a compare and swap on a single machine word. You can use this to program a lock, and give a lock a specification that says, that's going to enforce mutual exclusion and allow the lock to protect some resource that's described by some predicate and allow you to sort of synchronize between threads in this manner. And locks are just one instance. You can also program, I don't know, barriers and semaphores and condition variables and all kinds of other concurrency patterns just built on this foundation of separation logic with invariance. So I'll kind of stop there, and thank you for all your questions. I hope I didn't overwhelm you with too much code, but I thought it, and I hope you got some flavor of what Pulse looks like.
Yeah, thank you. Any final questions?
Does Pulse have support for reasoning about linearization points? It's a good question. There are many ways to do this. The way this in this separation logic frameworks, the way this usually works is through a technique called logical atomicity, and where effectively what you do is you kind of parameterize your code by ghost functions that that you run at a linear that will be run at a linearization point. So this is a whole topic in itself. The short answer is yes. The long answer is, well, I should say short answer is yes, though it's technically challenging.
So can you hear me?
Yeah.
So, I mean, you also said that you use Pulse to generate code for GPUs, right? I mean, am I right?
That's right. Yeah.
So what aspects of GPU programming have you bought in? I mean, like what was like?
So we have a model in Pulse of CUDA's partition memory, CPU memory, and GPU memory, and hierarchies of GPU memory, and the hierarchy of GPU threads, so blocks, warps, threads, and the synchronization devices among them. So the sync threads kind of barriers, the shuffle sync between warps. I think that's, yeah. So essentially, that's kind of the hierarchical model of CPU, GPU memory, and the hierarchies among the threads. We have models of that in Pulse, and then we write CUDA kernels in Pulse and prove them. They are by default data erase free and free of undefined behavior like overflow and so on, just by virtue of being in Pulse. And then we also prove them. We prove them functionally correct. So we have, functional correctness proofs about various gems and for various kinds of reduce parallel reductions and so on. So once you've done these proofs in Pulse, so that the GPU dialect of Pulse is called Kuiper. So if you do a proof in Kuiper about your GPU program, then you can and then once your proof is done, you extract it directly to CUDA. And some other kind of one of the the aspects of doing this in Kuiper is that you can also be very general. So you can write your matrix multiplication parameterized over any layout for each of the matrices. So you don't have to, write your program once for row major and once for column major, or you can just write it once and for all for any kind of layout, do your proof once and for all, and then and then specialize your program to different layouts, and and all with proofs. So you prove that your yeah, I don't know. Hopefully that's clear. Like you can be very generic and extract your program from Kuiper to CUDA.
Yeah, sorry, one last. So, is Pulse able to bring in that performance that GPU programs need to be
Yeah.
in terms of,
Yeah. So our goal is our goal is to be able to. I think there's no reason I don't see any fundamental reason why we should not be able to, because what you're doing in Kuiper is you're really writing exactly kind of the CUDA code that you expect. It's not that you're writing some, you're in some abstraction. You're writing exactly what you expect. We're modeling CUDA semantics, and you're writing exactly the code that you want. So you get the performance that you expect. So we're currently we're sort of trying to Kuiper is still it's still a work in progress. So our goal is to get to a point where we have a drop-in replacement for cuDLUS that is formally verified and whose performance is on par with, if not better than cuDLUS for each of its algorithms. Right now, we are for the main matrix multiplication, the GEMS, I think we're around 70% of cuDLUS. We're continuing to optimize our code, and I think we will eventually reach that. So yeah.
Thanks. Great. Thanks.
Vimala, why do we have at most one effectful computation in each line? It's not a fundamental restriction, I should say. I mean, this is what the Pulse checker enforces right now. I could easily imagine a future version of the Pulse checker that relaxes this restriction.
All right, perhaps we can take a pause there. Thank Nick
Link
again
in our
for
code.
taking time out, getting up early in the morning, and telling us about Pulse.
Thank you all. Thanks for coming, and it was fun. I'll paste before I sign off, let me paste a link to this code that.
Yeah, I think the chat will disappear.
Yeah, hold on. Tutorial. These are the programs I will show you today. I think the multiplication is in this one. Where's the multiplication? Yeah, I think the multiplication is in here. I should say that all the, what I was really showing you was a selection from, there's an online tutorial about Pulse about over here. Paste this link as well. And what I was showing you was essentially like a selection of examples that are taken from here. So, for instance, this various kinds of multiply by repeated addition is in the tutorial text with some explanation around it. So, if you're curious to learn more about Pulse, I would suggest looking through the tutorial. And of course, feel free to reach out with questions.
Okay, thank you.
All right, thank you.
Thanks, Nikhil.
Thank you.
Bye,
Bye.
everyone.
Bye.